Today we're talking about equations of motion, and we've done a fair bit of kinematics in methods, but we've done it with the variable t. Okay, so we've said velocity, acceleration, and displacement with regards to t. Okay, so here we're going to be looking at those variables, but with regards to x instead. All right, where x is the displacement. So we're saying what is the velocity with regards to displacement? What is the acceleration with regards to displacement? So I'll point out two examples they give us in the textbook. So about halfway down the page, the two bullet points. The speed of water in a river, okay, is going to be twice its displacement from the coast. So the further inland you go, the faster it's going to flow. All right, as it gets closer to the coast, it sort of spreads out a bit more. The flow rate slows down. Acceleration of an object in water is half its displacement from the surface. So the closer it is to the surface, the faster it's going to be moving. Okay, to convert between, and then I'll put two formulas up here. So it's just that sometimes it's useful to express velocity and acceleration in terms of displacement. So we've got the first one here. We've got an object moves with a velocity of half x squared, where x is the displacement and x is the displacement in meters. And we've got time is in seconds. Find the acceleration of the object. Okay, so we're going to be using one of these two formulas. Here we're starting with the velocity. So if we want to find the acceleration, this is the one that makes sense. So the acceleration is going to be v multiplied by dv on dx. So that's going to be half x squared multiplied by the derivative of velocity with regards to x. So when we differentiate this with regards to x, we're going to get half times 2x. Okay, so half's hanging out, the derivative of x squared is 2x, and then we simplify that to 1 on 2 x to the power of 3. Alright, so 2.5 ends up there, and x squared times x gives us x to the power of 3. So we've got the acceleration with regards to x. Okay, part B. Find the velocity and acceleration when the object is 4 meters left of origin. So they're saying, okay, for part B, displacement is 4. All right, we're 4 meters to the left. All right, we're 4 meters to the left. That means displacement is negative 4. All right, so we need to consider the direction of it. All right, we're 4 meters to the left. We've got negative 4. And so we want to find what is the acceleration and what is the velocity when it's at that location. Well, we've got velocity is equal to half times x squared. All right, so we're just going to process that one. Half of 16 is going to be 8 meters per second. And we've got acceleration is half x to the power of 3. So that's going to be half times minus 4 to the power of 3, which is 64 to minus 32. And acceleration in meters per second squared. Okay. Cool. So the first part, using that first formula, and then the rest just do a bit of substitution and processing. Alright, part 2, question 2. We've got an object with a displacement x accelerates at a rate of 3x root x meters per second. The object is initially at rest. Initial velocity is 0, and it is 4 centimeters to the right of origin. So its initial displacement is 4. Find the velocity function in terms of x. So we're given acceleration. Right, so we've got the acceleration function. It's 3x root x, so 3x to the power of 3. All right, straight away, let's put it in a form ready for us to integrate, differentiate, whichever one we're going to do. Now, we're starting with A, and we want B. Okay, so we're starting with A and we want B. So what we can do is we're going to start with this one and then integrate both sides. So I'm going to bring this statement over here first. So we have d on dx of half b squared is equal to A. And we've got the value of A. The value of A is 3x to the power of 3 on 2. Now we want to isolate b. We're trying to find the velocity function, so we're going to integrate both sides with respect to x. going to clearly show what's going on here. Integral of, what have we got? I'm going to write it out like this, and then half b squared with regards to x. And here, 3x with regards to x. Now here you can see we're going to have dx on the bottom and dx at the top. And so what that does is that cancels the integral process. So you shouldn't think of this and this as separate terms or separate functions, but the integral symbol and dx exist together. And so if we cancel the dx, we're cancelling the integral symbol. So basically what's happening, because we've got dx at the bottom, we're getting rid of that. We've got half b squared on the left-hand side. Okay, it's not a step we need to show. You can go straight from here to here, which is when we integrate this, so we've got x to the power of n, so it's going to be 3x to the 5 on 2, and we've got 2 on 5, plus c. Okay, and then all we're going to do is process that for v. We want v by itself, we want the velocity function by itself, so we're going to multiply both sides by 2, so we're going to get 6 to 12 on 5, x to the 5 on 2, plus c. The value of c is not changing, right? It's some number. We don't know what it is yet. We will determine it in a moment. And we have the square root of both sides. Okay, so there we've got the velocity function to begin with, but we've also got some initial conditions. So the initial conditions, what have we got? The object is initially at rest 4 centimeters to the right. So that means x is 4 and v is 0. The object is initially stationary, it's not moving, it's at rest, positive 4 displacement. So let's put that in to solve for this value of c. What we're going to have is we're going to have 0 equals the square root of 12 on 5, x to the 5 on 2. I think that's a 4. 4 to the 5 on 2 plus c. Alright, so you don't need to go through and try and isolate c by itself because you can see what the solution has to be. Alright, it has to be the negative of this in order to make the left-hand side equal the right-hand side. So we can just jump straight to c has to be negative 12 on 5, 4 to the power of 5 on 2. Okay, so once we've isolated c, we can sub it back in, we've got the velocity equation. It is the square root of 12 on 5, x to the 5 on 2, take 12 on 5, 4 to the 5 on 2. But you could evaluate that to a few figures if you wanted to. Here I'm going to leave it exactly, just so that our answer includes all decimal places. Alright, so that was part A. Okay, we've found the velocity function. Alright, part B says, determine the speed. Speed is magnitude of velocity. Determine the speed when the object is 10 centimeters right of origin. So when x is 10, what's the speed? So we'll calculate that. Alright, all we're doing is substituting the displacement is 10 into the velocity function and processing it. Here our answer is going to be positive. Alright, and because we're talking about speed, if it's negative, we make it positive anyway. We're not interested in its direction, we're just interested in the magnitude of it. So if we were to evaluate that, we'll get some significant figure, but for now we'll just leave it like that. Okay, and then part C, determine the displacement when the velocity is 8. Okay, so here we're thinking about our velocity equation. We've got velocity is 8 and we're interested in the variable x. So we've got 8 equals, and we've got 12 on 5, x to the 5 on 2. Take 12 on 5, 4 to the power of 5 on 2. Alright, and we're trying to isolate x. Right? So we can go through and do this one exactly, and maybe we will just to do some more algebraic operations. But a simple way would be to graph this function, right? This is a function of x, and then say, gsolve, what is the x value when the y value is 8? Okay, and that's going to bring up the solution for us. You can also put it in equation solver, although I'm reluctant to put it in equation solver when there's potential for more solutions. Because of the nature of this function, there won't be. All right, I'm aware of that as a math teacher, but for you guys, it's just safer to put it in the graphing because it brings up every possible solution. Okay, so let's go through and show this one manually. Let's find a manual solution to it. So I'll make the statement up here again. We have 8 is the square root of 12 on 5, x squared, take 12 on 5, 4 to the power of 5, that's 5 to 2, and then square root it. Okay, first thing we'll do, square both sides. So we're going to have 64. Alright, we're going to move, this is a number, we're going to bring that over to the other side here. Alright, you see we're just breaking it down to get x by itself. There we go, quick. Okay, we will multiply both sides by 5 on 12. Alright, to get rid of the number out front there. Alright, and at any of these steps you could, perform some simplification. Alright, so we've left the x to the 5 on 2. And then to get x by itself, we put both sides to the power of 2 on top of 5. So look at that nasty mess over here. 5 on 12, 64 plus 12 on 5, 4 to the 5 on 2, to the power of 2 on 5. Alright, so that would be the exact value. And if you were to put that one in your calculator, you're going to see that it correlates. It's the exact same as the one you would have taken over here. Okay, so most of that's just a bit of substitution and processing, right? And we're using these two formulas, aren't we? Okay, so if we start with velocity and we need to find acceleration, that's the one we're going to use. If we start with acceleration and we need to find velocity, that's the one we're going to use with integration. Okay, so 8 pi, let's give it a go.